Our topic is linear partial Gromov Wasserstein embedding. My name is Yikun Bai. So in this work, we present a new embedding technique which can project data from the distribution space to the function space under the setting of the partial Gromov Wasserstein problem. So first, a lot of real-world data, for example, the Euclidean space data, manifold data, or the graphic data can be modeled as a probability measure or distributions. And optimal transport is a popular mathematical tool which can measure the similarity between two probability distributions, and this is a mathematical formula. And theoretically, people can prove the optimal transport define a metric between the two probability measures. And the Gromov-Wasserstein problem is an extension of the classical optimal transport problem. In this setting, we can measure the similarity of two distributions in different space. So in particular, for example, the distribution mu is supported in space X, and we model it as a metric measure space, which is this tuple. The dx is the metric in this space. So dx tell you the structure information of this space. So GW problem is defined by this quadratic form with respect to the transportation plan gamma. And theoretically, we can prove GW problem is also a metric between the two spaces. However, unlike the classical OT, computation for GW generally require the so-called Frank-Wolf algorithm, and its complexity is n to the 7, where n is the size of the data set. So to improve the computation, some researchers present the so-called linear Gromov-Wasserstein embedding technique. So they consider the following problem. Suppose I have k different distributions, how to efficiently pairwise compute their GW distance. So their idea is first, find a reference measure, and for each target measure, we compute the GW transportation plan between the reference measure and the target measure. Suppose the transportation plan is given by this mapping, and we use this function, which can be treated as the displacement from the source domain to the target domain. So this displacement function, we call it a linear GW embedding. And given two such embeddings, if you compute their L2 distance and the result distance, we call it a linear GW distance. And numerically, the linear GW distance can be used to approximate the original GW distance. So the reason we construct this formulation is we reduce the computation, the pairwise the computation of GW distance to the following. So we need to run k times the Frank-Wolf algorithm to construct the embedding, and to pairwise compute their LGW distance, we just need k choose 2 times the quadratic of n. So it's much faster than pairwise compute the original GW distance for each pair. So our contribution is we extend the above formulation to the partial GW setting. So the partial GW, I explained it in another video. In one sentence, it is an unbalanced extension of the classical GW problem. In the new setting, some part of the mass, for example, at here, we select and transported to match the target, but some part of the mass in the source domain will not be transported, and some part of the target domain will not be matched. So this part will be destroyed, this part will be created. So in the partial GW setting, we construct the linear embedding in the following way. So the first term is the displacement, and it's same to the linear GW setting. And the second component is the part of transported mass in the source domain. So reference measure, I mean the source measure is given. I know the part which is transported, then I will also know the part which is not transported. And based on the first two components, I will know the part which is matched in the target domain. So I still need to record the information of the part which is not matched in the target domain. So this is defined by the following. So this tuple, we call it linear partial Gromov embedding. And given two such embeddings, we define this formula as the distance, and we call this distance as the linear partial Gromov Wasserstein distance. And we use this to approximate the original partial Gromov Wasserstein distance. So first, we prove that in some special technical setting, linear PGW also define metric. And in addition, we demonstrate its computation complexity. So we still need to run Frank-Wolf algorithm k times to get the k embeddings. And then for each pair of the embeddings, we just need n squared complexity to compute their distance. And this figure, we visualize the embedding. So this is the original data. And in the second row, we suppose the data is corrupted by some random noise. And so all these three columns represent the reconstructed data from the embedding. So you can see we compare the linear optimal transport embedding, the classical linear Gromov-Wasserstein embedding, and our linear partial Gromov-Wasserstein embedding. And because of the partial Gromov-Wasserstein properties, we can observe when we construct the embedding, most of the noise data is not incorporated. So when we reconstruct the data, this noise data disappeared. And in this figure, we show the MDS visualization for the PGW and the linear PGW. So all of this shape are the reference measure. So you can see if the reference measure we select is good, then the MDS reconstructed shape is similar, I mean, based on the LPGW is similar to the figure based on the PGW. So we use this figure to demonstrate the accuracy property of the proposed linear PGW distance. So finally, we apply the linear PGW to the digit classification task. So here we use the MINS data set. This is training data, this is testing data. And furthermore, we suppose the testing data is randomly rotated and are corrupted by some random noise. What we did is for all the data, we compute their different embeddings, like linear OT embedding, linear GW embedding, and our linear PGW embedding. And based on the embeddings, we train a classifier, for example, SVM or more advanced classifier, and we test the accuracy. So here we visualize the PCA result. So you can see this eta is the percentage of the noise. So suppose we have 50% of noise. Our LPGW embedding, you can see different class still have a good linear separability, but LGW and LOT is hard to distinguish different class because the noise corruption. And in this figure, we demonstrate the shape interpolation. So suppose we have a source shape and a target shape, and we want to know how the source shape convert to the target shape. And this one is the reference measure we select. So we utilize the GW barycenter, TGW barycenter, and LGW and LPGW interpolation. So the barycenter is some classical concept in optimal transport communities. It's just roughly speaking, it's just something like the center of two different measures. So here we can see the result based on GW and LGW. Most of the noise data is incorporated. However, for the figure based on PGW and LPGW, less noise data is included in the results. In addition, LPGW's computation is much faster because the main idea is we just need to compute the embedding in one time, and then we compute the interpolation between two embeddings, and based on the new embedding, we reconstruct the data. So this is why the linear GW PGW method is faster than the GW and the PGW. Okay, so thank you for watching.